Morning, everyone. I'm Naveena from the Department of Electronics and Communication Engineering at Government College of Engineering, Barbu. Today, I'm going to explain my internship project titled EV ADAS System, Real-Time Electric Vehicle Dashboard and Warning System. Okay, in this project, we monitor important vehicle parameters such as speed, battery percentage, motor temperature, torque, and range. We have also implemented ADAS features like collision warning and blind spot detection. Okay, this project we use these tools like STM32, 103C8 T6 Blue Pill, and PICSimLab, Python dashboard, and ultrasonic sensors. Okay, coming to the next. Okay, now, modern electronic vehicles also generate multiple sensor values like speed, battery percentage, and motor temperature. But the drawback is the driver face a difficult situation to monitor these all values at the same time. So, in our project, this solves this problem by creating a real-time EV dashboard with ADAS safety features. Okay, in this project, we divided into two, EV and ADAS. One is EV part and another one is ADAS part. Okay, ADAS means automatic driving assistance system. Okay, then move to next slide. What is the objectives of this project? In this project, monitor EV parameters in real time. Okay, by using a dashboard, we continuously monitoring the parameters like speed, SOC, what is the battery status, and motor temperature, range. We monitor simultaneously by using the dashboard and then detect front collisions. Okay, using the ultrasonic sensors, we also detect the collisions. Here we use three ultrasonic sensors, one for front and left and right. Okay, then display speed. Okay, as I tell, display speed, battery SOC, torque, and range. Also generate warning and fault alerts. Okay, we also implemented some faults and alarms. Okay, then stream data to the Python dashboard. All these data will update in the Python. Okay, move to the next slide. Okay, what are the tools are used in our project? Software. What are the software tools are required? First one is STM32 Cube ID. Okay, then it is very important. Okay, STM32 Cube ID where is essential for firmware development. Okay, then PICSimLab. Okay, here we not use physical hardware components. Only through the simulation, we done our internship project. Okay, that's why using the PICSimLab. It's actually a simulation tool. Okay, then Python. Okay, in dashboard in our project we use the Python dashboard. Then Matplotlib and PySerial. These are two libraries. Means Python libraries. By using Matplotlib, it create SOC bar and speed graphs, what then gauges for the visual implements in our dashboard. Then PySerial also comes under the Python library used for serial communication. Then move to the hardware tools. We required STM32 Blue Pill and three ultrasonic sensors ranges high H3 SR04 and potentiometers. Okay, here we use four potentiometers. One is for acceleration pedal and brake pedal and SOC. Last one is motor torque. Okay, we use potentiometers in PICSimLab. Okay, then we use LED also. These LEDs used for alarm indicators. We use four LEDs, red, blue, green, and yellow. We use four LEDs in our project. Then we go to the next slide. Is system architecture. Okay, the actual system architecture flow is a sensor, STM32 Blue Pill, and UART Python dashboard. In sensor, here we use ultrasonic sensors. Okay, these ultrasonic sensor calculate the or collect the data. Sensor work is collect the data, and these data will move to the Blue Pill board. Okay, then we wrote the code, and the data will be processed. Then the processed data will be moved to the Python dashboard by using a UART. What is mean by UART? UART means universal asynchronous receiver and transmitter. It is actually a protocol. Okay, this protocol used to processed data, used to transfer the processed data to the Python dashboard. Okay, this is the system architecture of our project. Then we will move to the next slide. What are the components using PICSimLab? Okay, as I tell, PICSimLab is used for simulation. Simulation purpose, we use PICSimLab. Okay, what are the components it need? First one, input components. Accelerator, as I said, acceleration potentiometer, brake for battery SOC and motor temperature. Okay, then ADAS sensors. We use 3 ultrasonic sensors. Okay, and one more thing, our project is divided into 2, EV and ADAS. Okay, we see detail in later slide. Okay, here we use 3 ultrasonic sensors and output components. It come LED, UART terminal and pin assignments are defined the design document. Okay, move to the next. Okay, in my internship journey, I learned what I learned. I will showcase in my slides. Okay, in 14-day internship journey, in first 2 days, what I done in first 2 days means I learned the basics of the blue pill board and the basics of the GPO pins and all. Install all the softwares that I required for by using this internship. Okay, I install STM32 Cube ID and PICSimLab. Okay, then day 3 and 4. I implement a program for ADC. Okay, in PICSimLab we use potentiometers. I said potentiometers actually it gives analog values, but our STM board is only accepts the digital inputs. That's why we're using the analog ADC, analog to digital converter. Our potentiometers gives us analog outputs, but our STM32 blue pill board takes only digital inputs. So that's why we use here the ADC. Okay, it converts the analog output from the potentiometer, gives a digital input to the STM32 blue pill board. Okay, and the ultrasonic sensors. Okay, we use ultrasonic sensors. Okay, let's see brief about ultrasonic sensors. Okay, in this sensor, it contains 2 pins, trigger and echo pin. Okay, initially trigger pin will low and give after a certain time we give a high input to the or 5 volt to the trigger pin. Okay, after 10 microsecond, after 10 microsecond it become low. Okay, then the sound waves were received from the echo pin. Okay, sound waves received from the echo pin and give high input to the echo pin. Okay, it remains high after certain time. Okay, then how long the time echo pin will remain stay at the high state, that time will be calculated. Using that calculated time, using the calculated time, we measure the distance using the distance formula. Okay, this is the way that we measure the distance. Okay, how does the obstacle is senses? Okay, okay, we see the how the ultrasonic sensors work. Okay, how it is detected the obstacle. Okay, if the obstacle is placed, okay, generally ultrasonic sensor it sends about 2 to 400 centimeter. We fix the one threshold value. If the calculated distance is above the threshold value, there is no obstacle detected. If the calculated distance is less than threshold value, and then it detects the obstacle is here. Okay, this is the work of the ultrasonic sensors. Here we use 3 ultrasonic sensors, one for front detection and right and left detection. Okay, then in day 5 and 6, I learned timers and EV control. Okay, timers play an important role in our project. Okay, here I use 3 timers, timer 1, 2 and 3. Okay, what is mean by timer? Why do we use the timer concept here means, okay, in our project there's so many different tasks are done. Example, EV part. In EV part we calculate distance, speed. In ADAS part we calculate collisions, BSD, blind spot detections. Okay, these are different tasks are done in our project. Okay, timers used to different tasks in done at specific time periods. Okay, this is the work of the timers. And also EV controller. Okay, then in day 7 and 8, fault manager and ADAS. Fault manager and ADAS we I learned in that 7 and 8. Okay, then in day 9 and 10, I learned about UART and testing. And 11 and 12, I learned Python dashboard. 13 and 4, I used to documentation and submission. Okay, I will go to the next slide. Okay, what are the features available in EV? Okay, in a EV, electric vehicle part, I measure the speed calculation and SOC estimation, torque calculation, range estimation by using 4 potentiometer values. What is that? One is acceleration pedal, one is brake pedal, another SOC and motor temperature. By using these 4 values, we also calculate some other parameters like speed, SOC, torque, range by using some physical formulas. Okay, then in EV features we include 3 modes: eco mode, normal mode, and sport mode. Okay, in eco mode means no batteries wastage. The what is that, vehicle is not moving in condition. This comes under the eco mode. And in normal mode, the torque will slightly increases. Okay, the battery drain is slightly decreased. Okay, in normal mode. In sport mode, the acceleration will rapidly increases and torque will rapidly increases, and the battery management, so SOC and the battery consume is higher, consume battery is higher in sport mode. Okay, these are the 3 modes are used in our project. Then next one is regenerative braking. What is mean by regenerative braking means when the brake is applied. Okay, when the brake is applied, acceleration will decrease. As we know, when the brake is applied, acceleration will decrease. Okay, then and also that what is that? Negative torque will created when the brake is applied. The negative torque will created in that. Okay, by using this negative torque, the SOC, the state of charge, will slightly increases. That means the battery also charged during the regenerative braking. Okay, that's why this name comes under the call regenerative braking. Okay, move to the ADAS features. Okay, in ADAS features, as I said, we only calculate the collision, means forward collisions and blind spot detections. Then time to collision calculation. Time to collision calculation means both forward and collision warning, blind spot detection comes under this TTC, time to collision calculation. Okay, or speed warning and warning conditions. Okay. Warning conditions means what? If the distance calculated by ultrasonic sensors is less than 50 centimeter, it arises as a warning. When the distance is less than 20 centimeter, it arises a critical warning. Okay, blind spot is below 30 centimeters, it also arises a warning. Okay, we move to the next, fault and alarm system. We also implemented a fault and alarm system in our project. Okay, what are the faults included? Okay, before that, we use 5 states in that project. What are the states are? Parked state, ready state, driving state, then regeneration state, and last one is fault state. Okay, in parked state. In this state, the acceleration will not on, motor is off condition, and vehicle is static. No movement in that, and all outputs are off. Only the UART heartbeat is active in this parked state. Okay, then when the acceleration is moves greater than 2%, then it shifted from parked state to ready state. In this condition, motor is armed and the vehicle is ready to move. Okay, motor is ready to move, and when the acceleration is more than 5%, it shifts to the driving mode. In this condition, the vehicle is moving state, vehicle in motion state. Then when the brake is applied greater than 10%, it moves to the regeneration state. As I said, In regeneration state, when the brake is applied, there is one negative torque will created. That torque will increases the SOC. Okay, when in driving mode, when the brake is applied greater than 10 percentage, it will shift to the automatically shift to the regeneration state. And that state, when the brake is less than 10 percentage, it will back to the driving state. Okay, then comes to the fault state. Okay, fault state will happen due to what? Motor overheating, low battery, collision detection, sensor timeout, and communication failure. Okay, these are the reasons that for fault happening, fault state happening. Okay, we see the alarms. Okay, here we have the three alarms on critical, warning, and advice. In critical alarm, when the collision is detected, when the forward collision by using ultrasonic sensors is detected, then the critical alarm will arise by using red LED. Then warning LED. Sorry, warning alarm. Warning alarm is indicated due to the motor temperature, high motor temperature, low SOC. Okay, these are the reasons for raising the LED indicators. And then advisory alarm, when it is used for BSD, when the blind spot detection distances come close to the vehicle, then the advisory alarm will arises. Okay, let me move to next slide. A Python dashboard. Okay, all the data will processed. Okay, all the data and parameters and calculations are done. Now the only thing is these process data will move to the dashboard. How it is works? How these data can be moved to the dashboard? Okay, what is the dashboard displays? Here we see dashboard displays the speedometer. Okay, speedometer that indicates what is the speed is going on the vehicle, and battery percentage. Okay, battery percentage and vehicle range, torque, motor temperature, ADAS bird eye view, fault alerts. These are displayed in what dashboard by using Matplotlib library. Okay, then move to the workflow. What is the workflow? Read ADC values. First thing, we read ADC values from potentiometers and update EV model. Okay, by using by using potentiometer values, we update the EV model. Okay, done. EV part is done. Come to the ADAS part. By using ultrasonic sensor, we calculate time to collision, collisions, BSD by using sensors. Okay, ADAS is done. Then measure distance, calculate TTC, generate alarms, control LEDs, and then UR data, update the dashboard. It is a workflow of our project. Then we move to the results. Okay, I achieved in this internship. What are the things I achieved? Okay, real time speed monitoring. Okay, this will achieved. Okay, driver, because the driver will difficult to monitor all the parameters at the same time. So that's why we include the dashboard by using real time speed monitoring. Okay, we monitoring speed, then SOC range at the same time by using the Python dashboard. Then battery SOC updates. Okay, then collision detection, then blind spot monitoring, fault handling, Python dashboard visualization, UR shell testing. Okay, these I achieved in my internship project. Now I'm going to demonstrate my project. I'm open the code that I have. Okay. It's a main.c. Here we have function definitions and key control.c. For.c. Okay, so many files, C files and header files and source files I have. This is the code I implemented. Then I open PICSimLab. Okay, this is the board, blue pill board. Okay, board, and here the blue pill option is here. Press it. Okay, this is a blue pill board. This is a series of blue pill STM32 F103 that show the demo like PICSimLab. This is my configuration vehicle. Okay. I reset first. Okay, as I said, I use here four potentiometers, one for acceleration pedal, brake pedal, SOC, and motor temperature. Okay, here I have four LEDs. One is critical, then two blue and green for advisory indicators, and yellow for warning. Okay, red LED for collision. Both green and blue for BSD left and green for BSD right. Okay, I have the IO virtual term. Here I see the values. What are the values here? AC speed is 20.1, SOC is 99.4, torque 0, temperature 22.7, range is 3316, acceleration 99, brake 1, fault is 240, F is 240. Then other data are mentioned here. Okay. Use three ultrasonic sensors, one for front and one for left and other for right. Okay. When the in forward collision warning, when the distance is less than 20 centimeter, uh, the critical alarm will rise and the warning alarm will also indicates. Okay, we see the IO virtual term. See. F distance means front distance 8, L is 296, R is 320, TTC 0.0, collision is 2. KBSD not detected. Alarm is 3. Okay, critical alarm indicates 3. Alarm 3. Fault is 4. Okay. We also reduces the BSD. Okay, when I reduce less than 30, it will, okay. Okay, it will indicate a blue. And this is that. What is the speed is available? Okay, and one more thing. For left and right BSD will activate when the speed is more than 20 kilometer. If once the speed is more than 20 kilometer, then only detect the BSD, blind spot detections. Below that, it not detect the blind spot detection. Okay. So green LED will blink. This is for right BSD right. Here blue is blink. This is that. Okay, these is a connection. I will move to the Python dashboard. For that, I use open virtual serial ports emulator. I choose what virtual pair. And next, choose comfort. It already selected the component comfort. It is enough. Okay, then we will open the command. Here we change the directory. I save my project files in workspace folder. So I chosen it. Please enter. Then Python. Name of the Python code evpython.py and port comma. Python evpython.py port comma. Please enter. Now the Python dashboard will open. It's the dashboard type C. Okay, here when the front ultrasonic sensor distance is reduced, here see the forward collision warning is detected. Okay, here we see in bird eye view the collision is detected. Then the speed C 21 kilometer and SOC will 95.7, and here it shows the speed graph. Okay, these are the EV metrics. What are this? Torque will okay. Torque is 148 Nm, acceleration is 99, brake 1%, motor temperature is 25, alarm, critical alarm, okay, when it is critical alarm, comes under critical alarm. Fault is okay, signal on. Then we move back to the PICSimLab. We move back in. Before BSD, I check the speed of my vehicle. Okay, what is the speed? Okay, 21.1. Now the BSD is working. Reduce. We will indicate. Now we see the dashboard. Below 30. Okay, here the blind spot is detected at the right side. Okay, let's see in bird eye view. Then I change these EV metrics values also. Back to this one. Okay, I decreases the acceleration and increases the brake. Now the negative torque will produce in that, and also reduces SOC. I increases the motor temperature, then the warning alarm is raised. You see the yellow is indicates a warning. We will move to the dashboard. We see the updated values.